Assalamualaikum and a very good evening to my respected lecturers and my fellow classmates. Today, I'm going to present my final year project titled Cardiac Abnormalities Detection using Deep Learning Method. My name is MARINI BINTI MANSOR, supervised under Dr. Diyana and co-supervised by Colonel Dr. Noor Ashikin. What is cardiac and what is cardiac abnormalities? Cardiac is an organ, which is the heart, responsible for pumping blood throughout the body. And cardiac abnormalities is congenital heart defects. In our project, we introduced the neural network to classify cardiac abnormalities, where we diagnose by tertiary classification. Heart disease is the leading cause of death, accounting for 1 in 5 deaths. According to the World Health Organization in 2022, cardiac abnormalities may be due to several factors, but lifestyle changes and medications can reduce the risk by 25 to 80% or more. It presents a formidable challenge for medical workers. Identifying these conditions is often fraught with difficulties, and delayed detection significantly diminishes the prospect of saving lives. The research question number 1 is, what classification model can be effectively proposed for analyzing cardiac abnormality data using supervised machine learning techniques? And the second research question is, how does the performance specifically in terms of accuracy of the proposed supervised machine learning models for cardiac abnormality classification compare to each other? The first objective of this study is to propose a classification model for cardiac abnormality data using supervised machine learning technique. The second objective is to compare the performance of these proposed supervised machine learning technique in terms of accuracy. The scope of this project revolves around the exploration of deep learning techniques with a particular emphasis on neural network, KNN, and fine tree using MATLAB software, where the data is taken from Malaysian Armed Forces. This study is about combining technology and medical knowledge. If it works, it could show how using smart machines can make medicine better. If we can make it quicker and easier to find these problems, it could save money and help more people to stay healthy. Here are some of the literature review related to the field of work. In the thesis titled Early Prediction in Classification of Cardiovascular Disease with Machine Learning, Neurofuzzy and Statistical Method, written by Osman Thailand and his team in 2023, by combining the machine learning, neurofuzzy and statistical method, it could outperform other well-known approaches, reaching a high prediction accuracy more than 90%. In 2023, Surjit and his team found that by using method neural network, random forest, Bayesian method, and C5.0, the accuracy is 99.1% compared to the Quest method, which the accuracy ranged from 68.7% to 86.6%. And the study by Hugo and his team discovered that the accuracy achieved by KNN ranged from 73.11% to 73.11%, while neural network achieved 99.26% and naive Bayes achieved 50.44%. Most of the previous studies showed that the neural network achieved the highest accuracy compared to other methods. To develop an accurate deep learning-based solution for cardiac abnormality detection using data from Military Medicine Department Hospital Angkatan Tentera Tuanku Mizan, the dataset will undergo quality enhancement through pre-processing and then using MATLAB to process the data. The model performance will be assessed by number of observation plot, true positive rates, and false negative rates, where the formula of TPR and FNR are as seen in the slide. Here is an example of raw data. As you can see in the data, there are a lot of attributes that do not contribute to the prediction of cardiac abnormalities. For example, tarikh appointment. From the raw data, we have 49 attributes which are taken from 2,140 milliliters. That totals up to 104,860 instances. But for processing, we only take 17 attributes from 2,092 milliliters, which total up to only 35,564 instances. So the attributes that were used are what we call predictors, including umur, which is age, BMI, body fat, systolic blood pressure, diastolic blood pressure, pulse, waist, T cholesterol, LDL cholesterol, HDL cholesterol, triglycerides, fasting blood glucose, and HbA1c. These are the neural network flowchart, which are for classification, regression, and video classification. But in our case, we are going to use classification. Neural network architectures refers to the structure and design of a neural network, which is a computational model inspired by the human brain. Neural networks are composed of layers of interconnected nodes, or neurons, used for classification. Input layer consists of nodes that represent the input features of the data. Each connection between nodes in adjacent layers has an associated weight, which the neural network learns during training. Between the input and output layers, there can be one or more hidden layers. These layers contain nodes that process the input data through weighted connections and apply activation functions to introduce nonlinearity. Softmax is an activation function used in the output layer of a neural network for multi-class classification problem. It is particularly useful when we want the network to output probabilities of each class. The softmax function takes a vector of raw scores, also called logits, from the previous layer and transforms them into a probability distribution. Results and analysis is the culmination of meticulous investigations guided by research questions from earlier chapters. The results of experiments and analyses tailored for cardiac abnormalities detection from the empirical core of the study, and it is the interpretive exploration. This is the accuracy for neural network model using the training data. It achieves the accuracy ranging from 79.4% to 83.4%, while for the test data, the accuracy achieves up to 90.3% with a maximum of 94.9%, which is the wide neural network. Overall, the consistent trend of higher accuracy on the testing set across models suggests that the neural network models generalize well to new data. The lower accuracy on the training set is considered normal, attributed to the model's exposure to noise and specificities in the training data that may not generalize perfectly. Wide neural network demonstrate accuracy on the validation set is commendable at 82.1% with a total cost of 267, indicating a good balance between accuracy and training efficiency. During testing phase, it significantly improves its accuracy, achieving an impressive 94.9% with a lower total cost of 109. The chosen hyperparameters align with the preset for a wide neural network featuring a single fully connected layer with a larger size of 100, ReLU activation, and an iteration limit of 1000. This is the true positive rate matrix for the training data. The number of true class 1 that is predicted as 1, which have the cardiac abnormalities present, is 7.9%, 88.1% and 4% are class 1, but classified as no cardiac abnormalities present and inconclusive respectively. In true class 2 and 3, no cardiac abnormalities present and inconclusive. There are 7.4% and 3.7% that are predicted as cardiac abnormal. So, the other four, which are 90.5%, 2.1%, 85.2%, and 11.1%, are classified correctly, and it is true negative, which is equivalent to 188.9%. For class 2, predicted as 2, which is no cardiac, is 90.5% for class 2. There are 3.7% and 11.1% that are predicted as 1 and 3, which is considered as false negative. 7.9%, 4%, 3.7% and 11.1% are true negative, which is equivalent to 26.7%. This is the test confusion matrix for true positive rate and false negative rate for wide neural network during testing phase. This is the various types of KNN accuracy during training phase, which range from 89.6% to the highest, which is 89.7%. Well, this is the accuracy of KNN during the testing phase, ranging from 89.7% to 89.8%. The accuracy validation for fine tree is 81.4%, while for the accuracy test is 91%. A detailed comparison between neural networks, KNN, and fine tree reveals nuanced differences impacting their performance. Deep learning exhibits shorter training times, superior accuracy, and eliminates some of the data processing that typically involve with machine learning, which makes it easier for the researcher to use machine learning, especially in handling intricate relationships within physiological data. Fine tree, although demonstrating commendable accuracy, may struggle with complex data sets containing a mix of categorical and numerical data. KNN, while simpler, faces similar challenges to fine tree.
However, the adaptability and ability of deep learning to capture intricate patterns make them superior for cardiac abnormalities prediction, and fine tree provides a balance with good accuracy. Each model's strengths contribute to a comprehensive approach in cardiac health analysis. Here, I have made the comparison between the performances of the three methods. As we can see here, the neural network achieved the highest accuracy compared to other methods. And the highest accuracy for the neural network is wide neural network, which is 94.5%. In conclusion, deep learning often outperforms other machine learning algorithms due to its ability to automatically learn intricate features and representations from data. Unlike many traditional machine learning methods, deep learning models, especially deep neural networks, exhibit a remarkable capacity to extract relevant features without extensive pre-processing. In the case of deep learning, data cleaning remains a crucial step ensuring the input information is accurate and reliable. On the contrary, various other machine learning algorithms typically require substantial pre-processing steps to handle tasks such as featuring scaling, handling missing values, or transforming categorical variables into a suitable format. The inherent capacity of deep learning to automatically learn hierarchical representations makes it an attractive choice for tasks where complex patterns and relationships are prevalent, potentially reducing the manual effort and domain expertise required for pre-processing. The superiority of neural networks over KNN and fine tree for cardiac abnormalities prediction, with recommendations for future research. Suggestions encompassing exploring hybrid models, fine-tuning, hyperparameters, and addressing class imbalance. Additionally, for future work, we aim to extend our analysis to incorporate both numerical and categorical data types, broadening the scope beyond numerical data alone. The research underscores the dynamic interplay between advanced analytics, machine learning, and healthcare, emphasizing the ongoing quest for improving prediction capabilities in cardiovascular health. This comprehensive exploration not only contributes valuable insights to the academic discourse, but also provides practical implications for healthcare workers and policymakers involved in the realm of cardiac health. Here are some of the references that I used for writing the thesis. That is all from me. Thank you.